Hi, this is lecture 19, and here we're going to go through some 1D pulse design examples, and we're going to talk about how, given that you have an RF pulse, how you can shift the excited volume, that is the volume that is excited by that pulse, so how you can shift it around in space. Okay, so first let's recall the small tip angle solution to the bulk equation. It says that the transverse magnetization at a time t and a spatial location r, remember that that's a vector, is equal to the integral over time of the RF pulse times this complex exponential phase function, right? And so it turns out to be a Fourier transform, and specifically we can define the excitation k-space trajectory of the RF pulse as k of tau comma t, right? So tau is the variable of time during the pulse, and t is the time at which we are evaluating the excitation at the end, and this is equal to minus gamma over 2 pi. We also defined it as we also pulled the 2 pi out here right before, but it can be in radians per Gauss, or sorry, radians per centimeter or cycles per centimeter. But the important thing is that it's proportional to gamma times the integral of g, and it specifically is the integral of t from the current point in time to the end of time, right? And so this is really the fundamental feature that is different between excitation and reception k-space. Okay, so then you can insert this into the above equation and get that the transverse magnetization excited by the pulse, evaluated at the end of the pulse at time t, is equal to I m0 times minus infinity times to t of gamma b1 times this complex exponential involving k-space here, right? So note that k-space here, the k-space trajectory here is in cycles per centimeter. Okay, and then we talked about this specific example from last time, right? We had a slice selective RF pulse, and then we played it out with a constant gradient waveform while the pulse was on, and then after the pulse ended, at this time, we switched the gradient to be negative, the same amplitude but negative, and on for half the duration of the original pulse. And so let's see, so this is RF, or B1 of t. This is G sub z of t. And this last guy here is going to be K sub z of tau. And if you call this guy T1 or T0 or whatever, tau comma T1. And then this axis is tau, actually. Okay, great. And so what happens during this pulse, we define these two segments, right? The segment 1 during which the RF is actually on, and segment 2 during which it is off, but there's still gradient playing out. And so during segment 1, we're depositing energy in k-space using the RF pulse, right? And we're moving along here according to the gradient, the remaining area under the gradient, and then zipping back at the end of time 2, right? So this first gradient leaves us at a positive kz location, right? But that corresponds to a phase roll across the slice, and that's going to cancel signal out, right? So what we got to do is we got to zip back to the center of k-space. That's refocusing the slice. That's called refocusing the slice. Okay. So then as the RF plays out, we are scanning across k-space, and then the rewinder returns us to the origin, right? And indeed it returns the entire deposition of energy to be centered at the origin. Okay. So now let's look at the evolution of magnetization during the pulse, or the evolution of k-space RF deposition during the pulse, to gain perhaps a little more intuitive understanding of what's going on here. Okay, so let's say that we've got this RF pulse as a time bandwidth 4 windowed sync function, right? And we're going to define these time points, T1 up to T7. So now let's consider these time points to be the end of the pulse, right? So let's look at the total energy deposition at each one of these time points, ignoring what's going to happen afterwards, right? Okay, so if we look at T1, this is time point T1, we have this excitation, right? So essentially we've deposited energy, this amount of energy here, or I'm sorry, we're looking at time point T2 here. This is T2. And we have deposited this energy, right? So the k-space for this, it starts at negative, and it ends up at 0, right? If we're stopping the pulse at this point. Okay, so then let's look at T3. So now T3 is also going to stop at 0, right? All of these x-axes are kz, right? Okay, so then kz at time point T3 we're here, and so now we have deposited this much, right? But again, if we're stopping the pulse here, then there's nothing left. We're observing what's happened at this point, and so there's nothing left for the gradients, and so now we just have this amount of area under the gradients. So we just start out further negative in kz, and we still end up at the origin, right? And indeed, it continues along this way for all these time points, right? So here's, let's do T4, T5, T6, and the really interesting one is, the really interesting ones are what happen at T6 and T7. It's a 7, okay. So then at T4 we've gone past the hump of the pulse, and so now we are back at, so we're about there, right? So we're starting now at a more negative frequency, and then at T5 we've actually played out the entire pulse, but everything is negative, right? So we actually, while we wanted to actually have deposited energy, we want the peak of the deposited energy to be at DC, at kz equals 0 here. It is not yet, right? So we need to play out some gradients to move it back to that point, right? And so then that's what we do with the second part of the pulse, right? And so we're going to look at time points T6 and T7 there. So then T6 is going to bring it back about halfway where we want to be, and T7 will finish the job, and will be centered at kz equals 0 there. Okay. So the result of all this then is that the RF goes in centered at DC, right? Or that is equivalently kz equals 0. Okay. So the gradients played out during the excitation. Played out after the excitation. Move that previously excited magnetization around, right? So we lay down the RF power, and then after we're done with the pulse, the gradient played out afterwards actually shift that whole previously excited magnetization around, the entire volume, right? So you can think then of the RF as writing an analog waveform in k-space, and the gradient determines exactly where we're writing it, and indeed can even manipulate it manipulate the position where we wrote it just as an affine shift, even after we have finished writing out the pulse. Okay, so let's look at some other 1D examples here that are kind of cool. All right, so let's look at, this is only a little bit different from the one we were just looking at. All we did here was just add another half area negative gradient encoding lobe on the beginning of the pulse this time, right? So let's start out, otherwise it's the same pulse, right? So we know what the trajectory is for the rest of the pulse. It goes like that, right? We've already drawn that before on the previous slide, right? So because of the lobe at the end, we nicely pass through through DC at the end of time, or in the middle of the pulse. Okay, and what the first guy is going to do is it's actually going to be, you can imagine it starts at 0, and then it goes negative, right? So it starts at 0 because the area of this entire, all this area, and this area, and this area, they all cancel out, right? So it starts at 0, and then it goes negative, and then it moves up positive again, and then goes negative again. Okay, so basically this is a balanced gradient lobe. Now you can imagine that if there's no magnetization sitting around here, then the gradient does nothing, right? It has nothing to cause to precess. So this only really you're going to be doing in situations where you have magnetization sitting around before your excitation pulse, right? So the two situations where this comes up are in spin echo and SSFP, right? Steady state free precession. These are two situations where you've already got magnetization hanging around from a previous excitation. And this waveform is called a balanced gradient waveform because it integrates to 0. And so again, what happens here is that the first gradient lobe, if let's say we define these regions, let's define this as region 1, this is region 2, and this is region 3, or segment 3, then segment 1 is going to move us out here. Then during segment 2 we're going to play out the RF pulse, and we're also going to be moving back in KZ, back positive in KZ, and then segment 3 is going to move us back to 0. Okay? And we'll talk more about why it is that everything has to be balanced in a spin echo pulse later on. Okay, now here's a curveball. So what happens in this pulse? So this pulse kind of looks like we took the first half of the lobe, then copied it over here, right? But it's kind of interesting what you end up getting out of this. We already know what the K-space trajectory looks like, right? For this guy, we've seen it before for the 1D slice selective pulse. It looks like that, right? Now, let's define 3 different time periods for this pulse to help us visualize what's going on. We'll define this guy, this guy, this guy, and this guy. Okay. And we've got time period 1, time period 2, and time period 3. Okay, and then we'll plot on the right here what happens for each of these time periods. Okay, so time period 1 starts out at negative KZ and moves up to 0, right? So we know that it's going to go like that. And the RF that's laid out during that time is half the pulse, like that, right? That's time segment 1. Okay, time segment 2, nothing happens, right? But we do go further, we go more positive in KZ. So we'll just draw that out here. And time segment 2, we go more positive. Okay, now what happens in time segment 3? Now we start out positive, and we go back to 0, right? So we start out where we left off with 2, and we go back to 0. And along that path, we lay out the following RF, right? If this is going in time, we'll lay out like that. So this is actually the same pulse as we had before. Right, so if you played out this pulse in the absence of field inhomogeneities and such, you would get the same slice selective excited slice as you got with the previous pulses. Okay, now how about this guy here? So this guy's pretty cool. So what happens here is we took that balanced gradient waveform that we had before, and we play out negative RF during the other negative lobes. So let's see what happens here. Let's define this guy, this time period, as 1. We'll define this time period as 2, and we'll define this one as 3. And we already saw the gradient waveform for this, right? It looks like this. You're just going to go down here and go positive, and then go back down to 0 in time segment 3. Okay. So then what do we have? We have during time segment 1, we're going to start out at 0 and go negative, right? So we can draw that on here. We're going to get to a negative KZ max there. And what are we playing? We are playing this negative pulse here, right? So it's going to start out like this, right? That's the K-space energy deposition. Okay, now in time segment 2, we're going to scan back positive, right? At the same time, we're going to play out this waveform. Alright, so we're going to be, this is 1, and then in 2 we're going to scan back. So now we have this guy, right, which is a full waveform there. Okay, so you can see here already that these two are going to cancel, this left-hand side is going to cancel out, and as you can imagine, in time segment 3 you can see that you start out positive and then go back to 0. So we'll draw that here. There's time segment 3, and at the same time we are playing again the negative of the other pulse, so it's going to look like that, and so these guys cancel out, and we get 0 excitation. Okay? I'm sure somebody could find a use for that, but it doesn't seem too useful. Okay, but one interesting case is the case of doing multiple excitations and then summing the data afterwards. So most acquisition methods require several repetitions to make an image, right? Like we have 128 phase encodes for Cartesian imaging, or we have 16 spiral interleaves, for example. right? And those are you collect data for each one of those leaves or phase encodes, and then you combine them afterwards. So then after collection, the data is combined to make an image. So the same idea, though, can work for excitation too. Okay, so here's a simple 1D example that is actually done in practice for short T2 imaging. So let's say that we split up our acquisition into these two repetitions, during which we play two halves of the two halves of a slice selective pulse. But we negate the gradient. We negate the slice select gradient between the two repetitions. So that's going to give us different k-space deposition, right? So in the first repetition, we are going to have, we're going to start at negative kz and go to 0, right? So we're going to be there. Now in the second one, we start at positive kz and go to 0. So we're going to be there, right? So we actually, with each of these, we lay down half of the pulse, half the k-space energy deposition. And so what we can do is we can sum the data from the two acquisitions, and the result will be the same resulting image as if we had a slice select, played out a slice select, a single slice select pulse. So, but the key here is that a 0 TE is possible, right? So we can actually start collecting data right here after the end of the pulse, right? And so then that's what's called an ultra short TE acquisition. The downside, of course, is that you have two acquisitions. There are other downside practical problems with this, but the main one is that the main theoretical downside is just that you have to make two acquisitions, so you lose a factor of 2 in imaging time. But again, the total effective excitation here, after you sum up the data, is going to be a normal slice selective RF pulse, right? Where this is what was laid down in repetition 1, and that's what was laid down in 2. Okay, so for the final topic here, we're going to talk about shifting the excited volume, right? So it's nice and peachy that we can excite these slices, but what if we want to take the same pulse that we've designed and shift the volume off isocenter in the scanner, right? If we're going to collect multiple slices, they're going to be spatially offset from each other, but we'd like to use the same pulse, and we just want to figure out how can we shift that excited slice so you get the same slice profile, but at different centered at different spatial locations. So far, and indeed in the homework 4, the slice has been centered at isocenter. So that's z equals 0 centimeters, right? But what if we want to shift it somewhere else? So let's say that we want to shift it to location R0, right? So that could be any point in XYZ space. Now mathematically, shifting the volume by this amount, R0, is equivalent to replacing the argument R, the variable R, with R minus R0. That will shift the entire excited volume by the amount R0. So as a sanity check, let's say that you have the center of your slice at 0 in the original unshifted excitation, and then let's say we shift it, and then we evaluate the excitation at R equals R0, then this argument, R minus R0, in the pattern, is going to be equal to 0, right? So then, you know, check. We know that replacing R with R minus R0 will shift the volume, right? Okay. So that's what we do here. We basically plug in R minus R0 for R in the small tip angle equation, and let's see what happens. Here's the small tip angle equation with just R replaced by R minus R0. Now what we can do here is we can move out the minus R0 from this term here, and we can split up the two complex exponentials, one that is a function only of R, and the other that is a function only of R0. Okay, so then if we combine the B1, our RF pulse, with this function here, what we get is a function of time only. So indeed, this is what we need to do to shift the slice. So we can shift the volume by a distance R0 by multiplying or modulating the RF pulse by this function, e to the I integral of the gradient times R0. Now this is equivalent to e to the minus I 2 pi k of tau t, where this is the excitation k-space trajectory, times R0. Right? So basically, if you can imagine that if you have a time-varying pulse, then the modulation actually needs to change. And that kind of makes sense because the frequency of R0 changes, right? Effectively what we want to do is make R0 seem like 0 to the pulse. So you need to actually, if your gradient is changing all the time during the pulse, then it makes sense that the frequency modulation would have to change too, because the frequency at R0 is changing. Okay, but this guy is very extremely simple for a constant gradient in one dimension, right? So it's worth visiting that special case. So in that case, we have that this integral, because g is a constant, gz of s is a constant function of time, then we get this guy, right? We get u the I gamma gz times t minus t times z0, right? Minus tau times times z0. And so then we can split up this this complex exponential into two terms, right? And so in the left term here corresponds to a frequency shift. And indeed what I put in the parentheses here is the frequency that you need to modulate your pulse by, right? So that's gamma, the frequency shift is for gamma gz times z0, right? So this is in centimeters, for example. This is in Gauss per centimeter, and this is in radians per second per Gauss, right? So Gauss cancels, centimeters cancels, and we're left with radians per second, the frequency. This other term is just a constant phase shift, right? Because remember that little t is the time at which we evaluate the excitation, and so that guy's a constant. It's not actually changing during the pulse, and there's no other term in here that changes during the pulse. And so you can usually neglect this phase term, actually. So basically all you need to do is multiply your RF pulse by this frequency modulation function if you have a constant gradient in one dimension. And that's it. Thanks.